mathematics. So look out for the conversions in this chapter, okay, in this question. That's normally there, even in the matric paper, that's where it normally gets asked. So let's say this is object A again and object B. No, it's quite boring, but it's fine. This one has a charge of plus 2,5 times. Oh, actually, we're not going to do that. This, like I just said, this could probably be like microcoulombs, and this will be minus 3,6 microcoulombs. We normally don't mix, but they can. That could be micro and that could be pico, but the thing is, then they might cancel. The one might become negligible. Okay, now, how on earth did this one get a positive charge in the first place? It lost electrons, yes. How did this one get a negative charge? It gained electrons. Okay. Now, normally what they ask you is they're going to be touched and then they move away from each other again. All right, so let's do that. We're going to touch them. So when they are touching each other, A and B are touching each other, remember they're going to share charge, even distribution of electrons. Now, electrons are always going to move from the one that's more negative to the one that's less negative. So where is it going to move? From A to B or B to A?
B to A.
From B to A. So electrons are going to move from B to A until they have even Stevens. How do I work out that new charge? Exactly. So that's the quickest way of doing it. We're going to add them. We're going to say plus 2,5 minus 3,6 divided by 2. And that gives me say again? So is it positive or negative? It's impossible.
Negative 0.55. Yeah, that's what I want.
Yeah, it cannot be a positive answer. Say again?
Negative
0.55.
Okay, so each of them will end up with a charge of minus 0,55 microcoulombs, 0,55 microcoulombs. If they just ask you what the new charge is, you don't have to do the conversion. You can if you want, but it's not important. It wasn't asked.
And will they not both be minus 0.55?
Absolutely. When they touch, they're sharing the charge. They have to end up equal. Yes, absolutely. And now, if you look at the difference between this one and this one, and the difference between this one and this one, it also has to be the same. Because the electrons that B lost, A gained. So it needs to always be the same. The difference must be the same. So now, if we look at the difference between these two, did A lose electrons or gain electrons? Gained electrons. So now we can say, okay, A gained how many coulombs of charge? And if we look at B, did B lose electrons or gain electrons? It lost. How many coulombs of charge? So the change, let's see what it is. So this one, whatever this one gained, this one must lose. So what's the difference here? And what's the difference here? It has to be the same, or otherwise you're doing something wrong. Cannot be again.
3.05.
What's happening with that calculator, Mazuba?
They're adding the exact
It's 2.5 minus bracket minus.
So this one lost 3,05 microcoulombs of electrons. So if you get the difference here, it's going to give you the same. So this one gained 3,05 microcoulombs of electrons. Still happy? Now what they normally ask you after this is how many electrons did A gain? Or how many electrons did B lose? It's going to be the same. So how are we going to work that out? We know that, so when they ask you for the number of electrons, you're going to look how many did they gain, how many did they lose. So you had to do this sum first. So let's do number of electrons lost by B. So then you're going to say, okay, I know it lost 3,05 microcoulombs. So 3,05 microcoulombs was lost. What is the charge on one electron?
1.6 times 10 to the minus 90.
Nice, you find that on your information sheet. But now I'm going to actually work with coulombs. So can I still leave it as microcoulombs? Now I have, when I work with the value, I now have to say times 10 to the minus 6. And then you're going to divide it by the charge on one electron. So 1,6 times 10 to the minus 19.
And what's 9 times 10 to the 9?
No, it's gravitation. Oh, that's Coulomb's constant. It's K. That's when you're doing the calculations for F. What?
1.6 times 10 to the minus 9.
Yes, this you get on the information sheet. So if you go and, guys, if they ask you for the number of electrons, it's always the change in charge over the charge of one electron. Same principle. What do you get?
1,91 times 10 to the 13.
1,91 times 10 to the 13 electrons. Does that make sense? That's millions. Electrons are tiny, tiny little things, remember? So yes, it makes sense. There are millions of them being transferred. When you shock yourself, you're being hit by millions of electrons. Done.
When is this like all will be the road for the exercise?
And the kilo was more calculated as F equals.
Oh yes. But that's plug and play.
That's plug and play.
So then I can now ask you, what is the force between A and B? Okay, so I can ask you to calculate the force between A and B. Then yes, you're going to say F is equal to K Q1 Q2 over R squared, and now you have to do the conversion. So this is, then you fill in the value, you calculate, then obviously I have to give you the distance, and you also need to convert that distance. Remember, if it's centimeters, or then you need to put it into meters, or millimeters, you need to put it into meters. So this would be our R, the distance between the two objects.
I must have like units.
F is always in newtons. So it's going to be your answer in newtons. If I ask you for the force on A, which direction will A be pulled?
Towards me.
Towards B, to the right. Which direction will B be pulled?
Towards A.
To the left. Which one will experience the greatest force? Trap, setting a trap.
Is it E?
Why?
Because like
Because
B.
don't take a report
It's the same. It's the force between Q1 and Q2. Newton's third law. If I push you, you push me. Okay, please remember that. It's just in opposite directions. So feels a force towards B, but B feels a force towards A. They are the same. Please remember the F of A on B is equal to the F of B on A due to Newton's third law, guys. If I push you, you push me. And that's why there's two charges in this calculation. The force depends on the size of both charges, not just one of them. And this would be left or right, depending on which object it would be. So the force of A on B would be on B. B is being pulled to the right. So A on B would be right. B on A would be left.